Hello, hi there. My name is Luis, and I am a lecturer in biostatistics at the School of Applied Mathematics, Getúlio Vargas Foundation in Rio. And this is joint work with Guido Moreira. He is a postdoctoral researcher at Minho University in Portugal. And today I'll be talking about adaptive truncation of an infinite series, of course, geared towards applications to statistics. Right, so let's get straight into what the problem is. So suppose you're confronted with computing something that looks like this, right? So for mu and nu positive, you're confronted with computing the sum. This is known to not have a closed form solution for most values of mu and nu. To those of you that are curious, this is the normalising constant of the Conway-Maxwell Poisson distribution. And this is here to illustrate a typical problem that you might encounter in statistics. So in this particular case, you are trying to compute the normalising constant of a probability mass function. So what we would like to have is some method that, given our summand here, will allow us to have an approximation of this sum, which is an infinite sum, that is within a certain error. In other words, we want to do controlled error truncation, right? You can't compute this to infinity, so we're going to have to truncate this. So you'd like to do that truncation in such a way so as to obtain some error below a pre-specified threshold. Good. Right. So there are many possible applications. Normalising constants are one of them, as I just mentioned. The other one, which is quite important, is marginalisation of discrete latent variables in statistical models. This has become an important thing. Well, it's always been an important thing, but it's become even more important in the Bayesian context with things like STAN. That is very efficient. It's a very efficient program or programming language for writing your models, but you can't write discrete latent variables because these are not differentiable quantities. So if you want to marginalize over these discrete latent variables, especially if they are unbounded, right, so lead to infinite sums, then you need some sort of technique. Other things that you might want to do is to compute raw and factorial moments for a particular random variable, discrete random variable. All of these things will, in some form or another, involve infinite sums. In particular, you can kind of represent the problem as some measurable function f and some PMF, not necessarily normalized. So you're trying to sum something that is a product of these two entities. Right. So what are our list of desires, right? So we would like to have little or no user input. We'd like to have provable guarantee. So when doing our truncation, we'd like to guarantee things mathematically. And we would like a numerically robust technique or methods, and that it would be easy for practitioners to implement. This is not necessarily excluding what I said first, right? Right. So as with most things in statistics, you're going to have to make some assumptions about what you're trying to approximate. And in particular, we're going to assume that these series is absolutely convergent, that it's non-negative. That's not a deal breaker, but it's going to make things easier for us later. And we're also going to assume that it passes the ratio test, meaning that if I take consecutive terms, right, and I take the limit of that ratio as n goes to infinity, that will give me a number between 0 and 1, meaning that the series will pass the ratio test. And we're also going to have to assume that it's decreasing which you might counter, is weird because PMFs are rarely strictly decreasing. But what you can do usually is that you can sum up to the mode, quote unquote, and exactly, right? And then just approximate the tail. So that's also not a deal breaker. Right, so I'm not going to read this result in detail, but the point is that with a little bit of theory, you can bound the true value S, right, of your sum between two partial sums, or between two partial functions of functions of partial sums. And we're going to use that theory to motivate a particular technique. Right, so, okay, so we've seen what the problem is, a little bit of theory, but now what is it that people can do, right, in practice, and what is it that they do, right? So we have three major approaches that we're going to be considering here. First one is what we call the naive approach. It might be a bit derogatory, but it's sum to threshold. So if you assume there's a threshold epsilon, whatever it is, and what you're going to do is you're going to sum until the terms are smaller than this epsilon, right? And what we can show is that when the limit, right, when the series passes the ratio test and the limit is less than a half, then this technique will give you a truncation, right, a truncated sum that is within epsilon of the true value. A second thing that you can do is what we call doubling, which basically amounts to you sum up to n, then you sum up to, let's say, 2n, and then you compare these two partial sums. And if their difference is less than epsilon, then you stop. And if the difference is bigger than epsilon, then you go to 4n, and you keep doing that up to a boundary of how many iterations maximum you're willing to do. That's what we call C-folding, because you don't need to double necessarily. You could do triple, or you could do something smaller. The point is that you compute partial sums and then you compare them. This might not seem like the smartest thing to do, but it is blazingly fast, right? This takes advantage of vectorization, so you can do this very, very fast. Now, the problem is that so far, at least, we couldn't find any guarantees for this. So there's no guarantee that this is going to give you the right answer. And the third thing is, kind of our new proposal is adaptive truncation. Using the lemma that I just showed you, but not discussed in detail, we can always guarantee that we're going to get an approximation within epsilon, no matter what the value for L is, as long as it's between 0 and 1, right? So this is what we call adaptive truncation. Right, so what have we done about this whole thing? Well, so the first thing that we did was to create a package in R called summer, and summer makes it really easy to compute an infinite sum in a robust way. So here I'll give you a small example for the Conway-Maxwell Poisson normalising concept, right? So summer comes with some precompiled functions. The unnormalized PMF for the Conway-Maxwell Poisson is one of them. And what we're doing here is we are calling this precompiled function, and we are giving it the parameters mu equals 2 and nu equals 2. And we are asking for an approximation of the true value, right, within 10 to the minus 10, right? And we are specifying 1,000 maximum iterations. For this particular problem, we know that when nu is 2, we know what the real answer is. It involves Bessel functions and whatnot. So in this case, we can compute the true value. And when we compare the true value and the approximate, our approximation, we get an error that's below the pre-specified threshold. So that's a good thing. Now, there are a couple of observations about this calculation. First of all, not all functions are precompiled in Summer, but I'm just going to talk about how you can do this. And you can also implement your function in pure R if that's the problem, or if that's a problem for you. And yeah, so the other thing is, because this is a general technique, we're not, this talk is not about the package only, it's about the technique, the paper that we're writing about this, and also the package. We also implemented these techniques that we have just talked about in Stan. So this lives in a different GitHub repository, and we hope that's going to be useful for other people trying to do their own marginalizations in Stan, when those marginalizations obviously can't be done in closed form. Right. So if you want performance code, or if you have performance code written in low-level languages such as C or C++, it's really easy to integrate our routines with your stuff. So here I'm giving you an example of a geometric sum. So I'm using RCPP, RC++, in this case, and it's as simple as including a dependence, to Summer, and implementing your own stuff in C, right? So you've implemented the summand, right? So the function you're trying to sum, and you've put that in C, and then you can call our function infinite sum that will decide automatically, right, whether to use the naive approach, the sum to threshold approach, or the adaptive truncation approach, based on the value of L, right? You do have to provide the value of L so far. So far we have developed things around you knowing what the value of the limit L is. Anyway, so Summer is able to take C code or C++ code and compute the sum in a numerically stable fashion with minimal useful user intervention. Right. So what are our parting messages in this for this talk? Well, computing infinite sums is not trivial. If you have a problem with an infinite sum, you can either try to solve it analytically in closed form, which is probably going to fail, or it's going to be very cumbersome. Or you can try and find a bespoke, a custom approximation that works for that problem. We've seen this with many different functions that we use every day, like the zeta function, Hurwitz Zeta function, and even the Conway-Maxwell normalising constant. All of these functions have bespoke approximations, but then you have to invest a lot of time trying to get that approximation in the first place. So that's not a trivial thing, but with a little bit of theory, elementary theory from infinite series, we can propose algorithms that are numerically stable and have provable guarantees, right? And we've provided both R and Stan implementations that are fast and robust. So Summer is all implemented in C, so it's quite fast to use. And as limitations of our approach so far and future work, I could mention that, well, I've already mentioned that you need to compute L. So you need to know what L is, and sometimes that's a difficult limit to compute. Certainly much easier, right, to compute than the actual infinite sum, but still something that we could possibly work on. And we can't at the moment handle arbitrary negative values, but we can, and we do, handle alternating series. So if you have an alternating series, like the series representation for sine of x, that can be done. So with that, I would like to thank you for your attention and hope that this entices some more discussion about infinite series and truncation and our package summer. Bye, thanks.